So let's dwell a little bit deeply and try to understand what is the general inverse kinematic problem like, and what are the nature of the solutions, why it is called as a slightly difficult problem than forward kinematics. And with this we will be able to understand that okay, the equation, when it is taken in a certain way, it looks very difficult, but if we are able to apply a certain another way, that we will see in the next section, and that is basically called as inverse kinematics. Not inverse kinematic, kinematic decoupling. So what we see here is that though the equation looks a difficult one to solve, when we try to see it in a different way like kinematic decoupling, we will be able to see that the answers are not so difficult. So on the way to understand why we are using decoupling method, we have to understand generally what is the inverse kinematic problem looking like and what is the nature of its solutions. Okay, so for that, first let us look at the inverse kinematic problem. The inverse kinematic problem itself is that given a 4 by 4 homogeneous transformation matrix of an n joint robot manipulator. We know that if there is a robot which is having n number of joints, the final transformation matrix connecting the end effector to the base frame will be given by a 4 by 4 homogeneous transformation matrix. So generally its form is, if suppose you are having n joints, then the end effector will be the nth frame. If you remember the DH convention, the end effector will be having the nth frame. So based on that, I can write that the homogeneous transformation matrix, which will look something like the transformation matrix connecting the nth frame, which is the end effector, to the base frame, which is the zero frame, is basically having a kind of structure which we have already seen previously, which is R11, R12, R13, and similarly if we write, we will get this. Then we are having the position matrix. We all know that this is the R matrix, so we can write it in short form as, we generally write it in short form as, it is an R matrix, which is a 3 by 3 matrix. So let me write it as 3 by 3, followed by a series of zeros. So I'll just write 0 for 3 zeros here. Then we are having a D matrix, which is having 3 columns and 3 rows and 1 column, and it is having a 1 in the bottom. So this is basically the transformation matrix. So from this, with a joint, so with n joint variables, with n joint variables, so given this we need to find, so I will write here, we need to find n joint variables, which I will now name it as q1 comma q2 comma all the way up to qn. Remember, q I have just mentioned first time. Generally I can say that if it's a revolute joint, it will be a theta. So suppose if you are having rp, then I will say that I want to find out theta 1, theta 2, d3. Why? Because p is prismatic joint and the joint variable is translatory motion, so it is d3. This I have written it as basically q1, q2 and q3. So that is what is q1, q2, q3. So we should not get confused of why I have introduced q. It's nothing, just so this is the problem. So once you have been given this, from this you have to find out the n joint variables. Now if you are having n things to find out from this transformation matrix, basically we will have equations and we will try to solve equations. So how many are there? Okay, that's So we can say that the problem is basically, so I will write it. So basically the problem is, so basically we need to find, we need to find the n joint variables, the joint variables from how many, from this transformation matrix, how many elements are there? See, we are having 0 0, no, 0 0 0 1. Here also it will be, you know, 0 0 0 1 only. That means that is not going to give us any help, so that part we can actually not take. Now how many remaining elements are there? How many remaining elements are there? The remaining elements that we are having is, if you would count it, the remaining elements will be this 9 by 9 rotation matrix. So there are, sorry, 3 by 3 rotation matrix which has 9 elements plus 3, so we are having 12 elements. Okay, so these 12 elements will help us give 12 equations. If you remember, when we had solved the equation, we had got something like, R11, we would have got something like cos theta 1 into sine theta 2 minus sine theta 1 cos theta 2. So, the equation of R11, just like that, we will have 9 equations here and 3 equations for dx, dy, dz. So, we will basically have 12 equations. Okay, and from that 12 equation, we need to find theta 1, theta 2, all these, q1, q2, all the way up to. So, basically, we need to find the n joint variables from 12 elements of 0 t n, that is the matrix, or these 12 actually form 12 non-linear trigonometric equations. So trigonometric equations. So that is the problem. So we are having 12 nonlinear trigonometric equations to solve to find out these n joint variables. Now let's take an example. Generally we say that we try to use a robot which is having 6 directions of freedom. So I am having a robot which is having 6 directions of freedom. Okay, that means there are 6 joints. So I need to find q1, q2 all the way up to q6. And for that I will have 12 equations. But actually, are these 12 equations really 12 equations? No, because if you remember, this R matrix was an orthogonal matrix. Okay, so I will write, but since R is orthogonal, out of this 9, there will be only 6 elements which are independent, sorry, 3 elements which are independent. But since R is orthogonal, out of 9 elements, only 3 will be independent. So we have 6 equations. So we have 6 equations and not 12. Okay, let me write that, 6 equations and not 12 equations. So from this R matrix, we will be able to take only 3. And dx and dy and dz, that 3. So totally we will have 6 equations from which we need to find out 6 unknowns. That's going to be a little bit problem, because the nature of the solution, now we will try to say something of the nature of the solution. Therefore, So let me write here itself. Therefore, the nature of the solution, the nature or how the solution looks like, the nature of the solution will be. So I will, try to see how the nature of the solution looks like. So I can say the first thing is that it is difficult to solve it because it's a not a linear equation, and it's not a closed form. It's not always a closed form. So first we will try to say that it's difficult to obtain closed form of equation. What is the meaning of closed form of equation? Closed form of equations are those equations which will have definite answers. Generally it is difficult to find equations which will have definite answers. So that is the first problem, that it is difficult to obtain closed form equations out of those 6 equations. And the second one is that the solution may or may not exist. Solution may or may not exist. May not exist. And that is where the problem comes most. Because if suppose you are given a position and orientation that the robotic hand has to reach, and we try to solve it, we are not having any solution, it just simply means that the end effector will not be able to reach at that position in that orientation. Maybe it will be able to reach in a certain form, in a certain orientation, but not in any arbitrary orientation. So that is another problem. Now even if you find a solution, the solution may not be unique. What is the meaning of that? Suppose I will explain it with the help of a diagram. Suppose if you are having a robotic arm which is having 2 links. So this is the first link and this is the second link, and there is the end effector connected to it, and I want the end effector to reach at this position. So I will mark the position. The same can be reached if I am going to make the 2 links point like this and like this, and the orientation is like this. So there exists a solution in which we will say that okay, the first one has to have an angle of theta 1 and the second one should have an angle of theta 2 for the position to reach here. Whereas here I will have another solution that if you keep the first link at this angle, let us say phi 1, and this at another angle, let's say phi 2, then you will be able to reach here. So there are 2 solutions here. One is theta 1, another is theta 2. Sorry, theta 1, theta 2, and another one is phi 1 and phi 2. So you can reach the same position using these 2 different joint variables. So even though we get a solution, the solution may not be unique. That is the third major problem that we have to see. Okay, so I will write that as the solution may not be unique. So solution may not be unique. You may have many different solutions, and the robot will now have to find out which one should it use so that the end effector reaches. Should it use the theta 1 theta 2 value or theta 1 or phi 1 phi 2 value? For that it has to understand what is the workspace. Okay, now so the next problem will be that if at all you find a solution, the another problem that we will be facing is that the solution or the end effector position should be within the workspace. So the fourth nature of the problem that I will write is that the end effector position should be within the workspace, should be within the workspace. Workspace, I will divide it into two. Workspace, I will just write that also so that people are able to understand. Workspace, I will divide it into two. I will divide it into two portions, or two different kind of workspace. One is called as the dexterous workspace. The second one is called as reachable workspace. What is the difference? Dexterous workspace means you can reach that position and the end effector can have any orientation. You want the end effector to face in one direction, another direction, it will reach that place and it will have any orientation that you want. Okay. Whereas a reachable workspace will reach that particular point. It will make the end effector reach that particular point, but you can never be sure about what is going to be the orientation. Only one or two orientations may be possible. Okay, if you extend your hand and you try to elongate your hand to the maximum position, then your wrist actually makes you able to orient the pen in any which direction, or the tool that is there in your hand, it will allow you to twist it or it will allow you to turn it, because you are having a dexterous workspace. If it is not dexterous, then you will be only able to reach that position, you will not be able to do anything else there. That is the difference between dexterous workspace and reachable workspace. In dexterous workspace, it is the position and all orientation will be possible there. Whereas in reachable workspace, you will have only position and one or two orientations possible. You will not be able to have all orientations possible. So with this much, I will close this, because that is the nature of the solution. And so I will just say that if you are trying to find out a solution, it is difficult to obtain a closed form of equation. If you get a closed form of equation, we either use an algebraic method to solve it or geometrical method to solve it. Now, the solution of that particular problem that we have just now defined, it may or may not exist, or the solution may exist but it not may be unique. It may have many different solutions and the robot may have to choose which is the best solution. And the fourth one is that the end effector position should be within the workspace. So these are the general nature of the solution of an inverse kinematic problem. And next we will try to see what is the decoupling, kinematic decoupling. Thank you.